Yes.
Great. So thanks, everybody. Yeah, I'm here to give an overview of NHC's hurricane forecast operations and products. And as Amanda mentioned, I'm the branch chief of the Hurricane Specialist Unit at NHC, so really appreciate the opportunity to talk to you all today. So just as a quick overview, NHC's tropical cyclone products really provide sort of the big picture overview of the storm. We're following the storm its entire life cycle from actually before it forms all the way through its demise, whether it dissipates or transitions to some type of other weather system. And we're making a forecast of where's the storm going, how strong is it, how big is the wind field, and we're looking at those large scale impacts from storm surge, rainfall, winds, tornadoes, rip currents, marine hazards. And the local impacts and information down to sort of that community level scale are really provided by local National Weather Service weather forecast offices in the United States and by the local meteorological services in other countries in our area of responsibility. So first, I just want to take you through sort of what our typical forecast cycle looks like. We operate on a 6-hour forecast cycle that starts at the synoptic time, so 0, 6, 12, and 18Z. So that process starts when we issue the tropical weather outlook that goes out at that time. That would also be the time we would issue an intermediate public advisory if we have a storm that's has land-based watches and warnings in effect, that we issue those intermediate advisories for. And at the synoptic time, that marks the beginning of our forecast cycle, where we're collecting the data from satellite, weather reconnaissance, other ships and buoys, land stations, and all of that, and basically analyzing the state of the tropical cyclone valid at that synoptic time. And that whole analysis process takes 45 minutes to an hour, and then we initialize the model guidance that we're going to be using to make the forecast, retrieve the model guidance back, and spend about the next hour or so actually making the forecast of the track, intensity, and size of the storm. And then by 2 hours into the process, we have a hurricane hotline coordination call with the rest of the National Weather Service offices, with the Navy, with other partners. And then in that last hour is basically after the forecast and hotline call are done, that's when we're preparing the advisory products and actually issuing the forecast. And then we can compile and issue this national tropical cyclone watch warning product shortly after the advisory deadline that pulls together all the tropical storm, hurricane, and storm surge watches and warnings in effect for the United States into one single product. And then that whole cycle begins at 6 hours later. So we're continuously doing this for every storm in our area of responsibility. So start first with the tropical weather outlook. It's a product many of you may be familiar with. It used to be, many years ago, it was just a text product. It only really covered the next sort of day or two and talked about the development of disturbances in a very qualitative kind of way, using sort of phrases that talked about a tropical depression could form or some slow developments expected. Well, now we've transitioned to a graphical product, and we have actually probabilities of formation. So we have a 2-day graphic that we issue, and this is again issued every 6 hours. And on the graphic, you'll see the location of any disturbances we're talking about. So these are any systems that could become a tropical cyclone within the next 48 hours. So they're indicated in this particular example by an X. So we have a red X here in the central tropical Atlantic, a yellow X over a tropical wave that's about to come off the west coast of Africa. And we provide a probabilistic forecast of the chance that these systems would go on and become a tropical depression or tropical storm during the next 48 hours. Every 10%, so you can see this system 1 has an 80% chance, system 2 has a 20% chance, and they're also binned into categories, low, medium, and high. And then we have a 5-day probability and a 5-day graphic that shows the formation, where formation could occur in the next 5 days. We'll have systems on this graphic that don't actually exist yet in some cases, so we may just have an area. If the system does exist, it'll have an X on there. But the color shading of the development areas is done by the formation chance. So again, there's a probabilistic chance of formation for this system during the next 5 days in this graphic. And it also gives you an idea with these shaded areas of where we expect that formation could occur. So again, this is issued every 6 hours. It's going to constantly keep you updated over about where tropical cyclones could develop during the next 5-day period. And this is a routine product that's issued during hurricane season, and we also issue them out of season as necessary. So now when we get into the forecast process for actual tropical cyclones, we have to start off with an analysis, and we have to answer 3 important questions. we have to first know where is the storm located, what's the latitude and longitude of the center, and from this initial position, we can then compute the motion of the storm, which tells us something about what the steering mechanisms are and where the storm might go in the very short term, next few hours. Then we have to analyze how strong the storm is. What are the maximum sustained winds, which are basically a 10-meter, 1-minute wind associated with the circulation of the storm. And that can be arrived at in a variety of ways, from satellite intensity estimates to aircraft data to ships and buoys to scatterometers. But this is one of the questions we have to answer. And then finally, we have to know how big the storm is. What's the extent of the tropical storm and hurricane force wind field? And for this, we use things like ships and buoys and aircraft and scatterometer data to try to piece together what you'll see is a pretty crude estimate of the wind field associated with the tropical cyclone. Now, let's talk about the analysis uncertainty. So we talked about where we have to analyze where the center of the storm is now. Now, our confidence in where the center of the storm is located depends on a few things. It depends on how well defined or how easy to track the center is, sort of the development stage of the storm. So tropical storms may be very difficult to find the center, especially at night if you don't have visible satellite imagery or aircraft data available or a scatterometer. You're trying to infer things from infrared satellite imagery. So our location might only be good to within 25 to 45 nautical miles. For hurricanes, it typically gets a little easier, especially hurricanes once they develop an eye. You can see that the initial position uncertainty is about 15 to 40 nautical miles for hurricanes, and then major hurricanes, which almost always have a well-defined eye, the analysis uncertainty goes down to about 15 to 20 nautical miles. But we're never really exactly sure down to obviously the nearest 5 miles, where the storm is at a given time. So there's uncertainty even in the analysis that then plays into the track forecast. In terms of our intensity estimates, we think they're good to within about 10%, even when we have aircraft reconnaissance data, because sometimes we have conflicting sources of data that might suggest a storm is stronger or weaker, depending on what data source we're looking at. And we have to weigh the strengths and weaknesses of all those different pieces of data and come up with what we think is the best analysis of the storm's intensity, both in real time and in post-analysis. So that means if we're going out and saying that a storm is a 100-knot hurricane, it could certainly very easily be 90 knots or 110 knots. That's all sort of within the margin of error of just the analysis of the intensity of the storm. And then in terms of the size, again, we're specifying the tropical storm and hurricane force winds in these quadrant radii. So what's the maximum extent of tropical storm force winds or hurricane force winds in each of the 4 quadrants around the storm? For tropical storm force winds, we think those analyses are good to within about 25%. For hurricane force wind radii, they're only good to probably within about 40%, especially if we don't have aircraft reconnaissance, because aircraft is really the only way we can get a real adequate handle on the size of the hurricane force wind field, because it typically covers a very small area. You don't have a lot of other data. You're hoping ships are out of the way. Scatterometers can't really resolve those types of winds. And ships and buoys or buoy data in those types of areas are very sparse. So without aircraft data, the hurricane force wind field is a bigger question mark. Here's again looking at the wind radii. So the wind radii represent the maximum extent of the winds in a particular quadrant. And this is going to be found in the Tropical Cyclone Forecast Advisory. And again, it doesn't mean that those winds cover that entire area. So in this particular system, we think the 34-knot winds in the northeast quadrant go out as far as 160 nautical miles from the center. But that doesn't mean there's a continuous area of tropical storm force winds extending out that far. In reality, the wind field of a tropical cyclone is pretty highly variable in space and time. It has to do with the rain band structure, the motion of the storm, convective, how the thunderstorm activity is pulsing with time. So you may have a big band of tropical storm force winds that go out 100 nautical miles in a continuous fashion. Then there might be a break, and then there might be a rain band farther out that has tropical storm force winds in it that's separated from that inner part of the wind field. So again, this is a very crude estimate, and this is also how we provide the wind radii forecast as well. But the wind radii are very important because they obviously are telling folks where there are going to be hazardous wind conditions. They're important to how we lay out watches and warnings for land areas, the areas that those watches and warnings are going to cover. And then obviously they're very important to the marine community, especially trying to avoid that 34-knot wind area. Now let's talk about the actual forecasting. So forecasting tropical cyclone track is a relatively simple problem compared to forecasting intensity. So to a first approximation, a tropical storm or hurricane moves around in the atmosphere like a cork in the stream. There are these large scale atmospheric features like these big troughs and ridges that basically steer the hurricane around. And these features are pretty big and they're pretty easy to measure from our satellites and other observing systems. And the numerical weather prediction models that we use to forecast just day-to-day weather across the globe do a really good job of forecasting the evolution of these features. So because of that, we're able to forecast tropical cyclone track pretty well. And the track forecasts have been continually improving for many, many years, mainly because of improvements to numerical modeling. Now, forecasting intensity is a lot more complicated because it's not just figuring out what the large scale atmosphere is going to do. Now you have to understand what's going on in the core of the site of the hurricane, how the thunderstorm activity is evolving in the core, the interaction between the atmosphere and the ocean. You have to get the track right, because if you don't get the track right, you're going to put the hurricane over a different area of ocean that might have different sea surface temperatures. You might have the storm move over land or not move over land, which is obviously going to have a big impact on the intensity forecast. You have to know what sort of environment the storm's moving into. Is it an environment where the vertical wind shear is stronger or weaker? And how is that going to play into intensification? And then we also have these internal processes like eyewall replacement cycles that we can observe, but are really difficult to forecast because we can't pinpoint exactly when they're going to start and end and what their exact impact on the intensity of the storm is going to be. In terms of forecasting wind radii or size, there's really not a whole lot of guidance available. We have some climatology and persistence models that we use. We have some dynamical models like global forecast models that have some skill in telling us if a storm's going to be really large or really small, especially once they move out of the deep tropics and into the mid-latitudes. But in reality, we still don't have a lot of great guidance for forecasting storm size. So when we make changes to the size forecast, we're really trying to capture these sort of big picture ideas. You know, is the storm strengthening or weakening? How's the wind field going to respond to that? Is the storm becoming extratropical? Does that mean the wind field's going to expand? Will part of the circulation be over land so that the radii in those quadrants would decrease because of the increased friction over land? And what's the storm motion looking like? Is it moving quicker in one direction? Is the motion or direction of motion changing so that the storm's wind field is going to be lopsided in certain situations? So we're trying to capture these sort of bulk characteristics of the wind field. We're not going to be able to capture these details that are happening on an hour by hour or mile by mile basis with the wind field itself, even though we know that's how the wind field is evolving in space and time. Now going back to track, I talked about how the track forecast errors have been steadily improving. So this is a chart showing the average track forecast error in the Atlantic Basin for tropical storms and hurricanes, averaged together by decade. So on the x-axis here, you have the forecast hour, so from 12 hours out to 120. And then on the y-axis, you have the average track error in nautical miles. So you can see that, let's look at 72 hours here. You can see that in the 1960s, 70s, and 80s, there was a slow improvement in track forecasting. You can see the average track forecast error in the 1960s at 3 days was over 400 nautical miles. It was down below 350 nautical miles by the 1980s. Then there was a huge reduction down below 250 nautical miles by the 1990s. Around 150 nautical miles in the first decade of this century, and now down to about 100 nautical miles in the last decade. So we've seen tremendous improvements here, very steady, again, as numerical modeling has improved. The data that was getting into the models from satellites and other sources has improved as well. We're figuring out better ways to use the data. And then the models themselves are run at a high enough resolution that they're actually able to see the structure of the tropical storm and hurricane now that 20 or 30 years ago, many global models would have struggled to even know there might have been a tropical storm or hurricane there in the analysis or in the forecast. So now that the models can know that the storm's there and are doing a better job with the large scale steering pattern, that's why we're seeing these dramatic decreases with time in track forecast error. Here's just a graphical depiction of how the 3-day average NHC track forecast error has changed since 1990. So if in 1990, if we made a 3-day forecast, and our forecast point was here over the central Mississippi coast, the average forecast error at that time meant that the center of the storm could have been anywhere inside this blue circle. So that stretches everywhere from the Houston, Galveston area all the way east to the Big Bend of Florida in terms of where the center might cross the coast. Now jump ahead to today. We've cut that area probably by 75% or so. Now, if we put a forecast at 3 days here in southern Mississippi, the average error would suggest that the storm should be somewhere in the vicinity from southwestern Louisiana all the way over to the extreme western Florida panhandle. So we've made dramatic improvements in the average track forecast error, but we're still not good enough to be able to tell you 3 days out if a certain location is going to be impacted by the core of a major hurricane and the very worst storm surge and wind and rain conditions. The uncertainty here, even 3 days out, means a huge difference if the storm moves over on the right side of this average error or the left side, or stays near the official forecast. For what could occur at any one given location, it's very difficult to pinpoint that down to you're maybe within 24 or even sometimes 12 hours before landfall. Here are the current NHC track forecast errors. They increase about 30 to 40 nautical miles per day. And this is the average over the last 5 years, 2015 to 2019. So you can see that at 1 day, our average track forecast errors of 37 nautical miles, 96 nautical miles at day 3, and 172 nautical miles at day 5. Now, again, these are just averages. So there are a lot of forecasts that have errors smaller than this and a lot that have errors larger than this. So it doesn't mean that every 3-day forecast is going to have an error of less than 100 nautical miles. That's certainly not the case, and we can and still do make large track forecast errors in some situations. So what tools do we use to make the track forecast? So as I mentioned, modeling, numerical weather modeling has made tremendous advances, and they are the tools that we use to make our forecasts. So many of you have probably seen these types of plots before, these types of spaghetti plots. They're available all over the internet, and they're showing the tracks of a given storm from various different models, all these different colored lines and all these different 4-letter identifiers that you may or may not know what the models are and what they mean and which ones are any good. So when you look at a plot like this, you have to be very careful because you don't know a few things. You don't really know if these models actually are conveying the true uncertainty in the track forecast. You may not know that some of these models are not ones that we actually use to make a forecast and aren't any good. Some of the best performing models may not be on these publicly available model plots as well, guidance that we have when we're making the forecast at NHC. So the types of models we use really vary. We have things like extrapolation, which is on these model plots, and all that is telling you how the storm's going to move if it keeps on moving at its current motion over the next 5 days. And this can occasionally be useful if the models aren't handling the motion of the storm well right now. It might give you an idea of where the storm might be in 6 hours or 12 hours. But there's really no utility beyond that because the atmosphere is always changing and evolving, and what's going on now is not going to really be representative of what's going on even a few hours from now, and certainly not a few days from now. But that's on these model plots. We have a model that's climatology and persistence, and that typically just tells you what a storm in this location of this strength at this time of year, how it would typically move. And the only thing we use this for is a baseline to compare other forecasts against. So if you're not beating climatology and persistence, your forecast doesn't have any skill. And it's not something we use as a forecast tool, but it's on these model plots as well. Now we'll get into some of the more useful pieces of guidance. We have global models that are, again, these models that forecast just day-to-day weather globally, models like the GFS or the ECMWF or the UK Met. And these models are individually the best models we have for forecasting tropical cyclone track. And that's because they do a really good job handling the large-scale weather patterns and the steering flow that moves a hurricane around. Despite the fact that they're not really developed specifically for forecasting hurricanes, they're just forecasting the day-to-day weather everywhere, but they do a really nice job with that. Now, there can be issues with these models, however. They sometimes struggle to depict or appropriately resolve the details of the inner core of a hurricane. They don't have enough resolution to really see that yet. And they sometimes struggle with the structure of the storm and its intensity. The storm might be too weak or too strong in one of these global models or too small, and that can affect the track forecast. In fact, some of our largest track forecast errors occur in these situations where there's uncertainty about the structure of the storm and how it's going to respond to the steering flow in different situations. We also have regional hurricane models like the HWRF or the HMON or COAMPS-TC. And these are models that are developed specifically for forecasting hurricanes. They run at very high resolution, so they should be able to do a better job of handling the interactions between the tropical cyclone and the environment. But they've really lagged the global models in forecasting track. They're better for intensity. They sometimes have struggle with depicting the initial state of the hurricane properly. And they also are run over a smaller area. They're not run over the whole globe because of computational limitations. So if there are important features that are outside of their area that this model can see, that can degrade the longer range track forecast in some cases. Now we get to so-called consensus models, which are combinations of various models that are either averaged together or weighted in some way. And these are typically our best pieces of track guidance. They tend to cancel out the random errors that are associated with the different models that go into them, especially if the models are pretty independent of each other. And if they're showing a similar forecast scenario, they're going to sort of cancel out that noise. And they typically produce the smallest track forecast errors, and they're typically the starting point for the NHC forecast. But this type of scenario or this type of method doesn't work really well when the different models have very distinct track scenarios. So if there's one camp of models that has a forecast to the left, and another camp that is a forecast way to the right, the answer is probably not going to be what you would get by averaging those together. It's going to be one camp or the other. Thankfully, this type of scenario doesn't happen all that often, but it's one of the other ones that can lead to very large uncertainty and very large track forecast errors. I want to talk about continuity because that's something that's an important part of the NHC track forecast philosophy. So we're really have a strong constraint from the previous forecast that's being exerted on how much we're going to change the forecast in the current forecast cycle. We can't damage our credibility by making these big changes from one forecast to the next if the models are flip-flopping around. We can't make a big adjustment to the right and then the next forecast have to make a big adjustment back to the left again. So we typically make changes to the previous forecast in these sort of small increments. So we'll sort of gradually nudge the track to the left or to the right. And we really want to see consistent changes to the model guidance. If there's a big change in the guidance, we're going to wait and see if it holds for several cycles before we go on and make a big change, because we want to make sure we're making that adjustment in the right direction. And as a result, the NHC forecasts are often slower to reflect big changes than the model guidance. However, if you look at this graphic, this is an interesting chart that we put together this year. And what it's showing is for the three best global models for track, the UK Met, the GFS, and the European, what you're looking at is their 96-hour track error here on the y-axis, and their consistency from cycle to cycle at 96 hours on the x-axis. And this is from the Atlantic Basin at 96 hours for the last 3 hurricane seasons. So what you can see is that the NHC forecast not only has a lower track forecast error than these 3 models do individually at 96 hours, but the NHC forecast is also more consistent by a fair bit. So the average amount that the NHC forecast changes at 96 hours is about 60 or 65 nautical miles. The European changes by probably 80, the UK Met and the GFS are changing by about 100 nautical miles. So in addition to the NHC forecast having smaller error, the NHC forecast is also more consistent, and that's a really important part of what we provide. We're not always going to beat the models, but we're going to often, almost always be more consistent than the models and make changes in a very measured way, which makes the forecast more useful for our customers. Now we can look at whether NHC's intensity forecasts are improving. For track, we saw that steady improvement over many, many decades. Well, for intensity, this is a similar kind of chart with the average intensity error color-coded by decade. The story for from the 1970s up even until the last decade of the first decade of the 2000s was that the track forecast, the intensity forecast errors really weren't getting any better. There was some very, very slow minor progress, but almost just a knot or two here or there over the course of 30 or 40 years. However, in the last decade, we made some substantial improvements, especially at 36 hours and beyond. You can see that the average intensity error at 72 hours went from being about 17 knots down to about 13 or 14 knots. So that's a 3 or 4, 5 nautical mile, or 3 or 4 or 5 knot in reduction in the average intensity error, which is a pretty remarkable development for, and it's in large part due to improvements in the regional hurricane modeling like the HWRF, which has made tremendous strides in the last few years and now is is our best intensity guidance that we have to make a forecast with. Now, our average intensity errors over the past 5 years, these average intensity errors go up pretty quickly. At day 1, we're at 8 knots, 11 knots at day 2, and then they sort of level off at around 13 or 14 knots at days 3, 4, and 5. But again, these are average errors. A lot of the errors are a lot smaller than this. Some of the errors are a lot bigger than this in cases where we miss a rapidly intensifying storm. For example, we can rack up 30, 40 knot errors at certain times. So before I move on to the products, this might be a good time to stop and see if there are any questions about sort of our analysis and forecast process and the tools we use. So I'll let Amanda see if there are any questions from anyone.
Yes, we have several questions. First, Kathleen Creel asked on slide 9 what millbar chart was referenced. Is it 200 millbars?
On slide 9?
Yeah.
Let's see. Up the top figure, I think that's a multi-level plot. So it's got 850 millibar relative vorticity shaded, 500 millibar heights in blue, and 200 millibar winds in the wind barbs.
Okay. David Disbro asked a couple of questions. What are the relative strengths and weaknesses inherent in the different models, and how is the decision to emphasize one model over another made?
Well, the models change every year, so there isn't really time to figure out if models have these distinct biases. When 20 years ago, when the models only changed every 4 or 5 years, you could sort of figure out what sort of biases they might have and what their real strengths and weaknesses were. Now the models are really undergoing upgrades almost constantly. So the model was the best model last year. It doesn't necessarily mean it's going to be the best model this year. So we try not to pick model favorites when we're making the forecast, because even from storm to storm within a given season, the performance of one model can vary tremendously. So that's why we start with that consensus approach, where we look at the performance of the track models and we pick the best 5 or 6, and we use a blend of those as our starting point. Now, there may be a situation where you're very sure that a model has a very poor forecast if it doesn't have a good representation of the storm initially, for example, or if the steering flow in it is particularly bad, and you might de-emphasize that. But those are pretty rare occasions. Most of the time, the models have the sort of they all have a slightly different take on the same overall picture. So that's where sort of that blending together gives you the best forecast.
And then his second question is, please describe how to use the new storm surge forecast.
Okay, I might get to that later. So.
Okay.
Yeah.
Then we have a question from Jeff Lorenz. How long does it take for the specialized hurricane models to run, and are all of these models hosted at NHC?
The regional hurricane models like HWRF take several hours to run. So when we initialize a 12Z run of the HWRF, it's going to be available by around 18Z. But those all run on the WCOS supercomputer. So we just pull in the output from those. But we do take the steps to initialize and set up those models and provide the input to them for the storm where it's located. For example, some of the other regional hurricane models we use are run by the Navy and by other folks, and we pull that output in.
And he also asked, how does the model skill compare for the Eastern Pacific?
The model skill, it depends. In the Eastern Pacific, the track forecasting is generally simpler. There's less influence from the mid-latitude flow there because of the strong SST gradient, and storms don't get very far north in the Eastern Pacific before they die out. So almost any model most models do better in the Eastern Pacific. The average track forecast errors are typically smaller. In intensity, there's more rapid intensification sometimes in the Eastern Pacific, but there's less land interaction. Again, because the track forecasting is relatively easier, the intensity forecast errors can be lower at times because you're really trying to forecast when's the storm going to hit the SST gradient. But in a year like last year, we had some really high intensity forecast errors in the Eastern Pacific because we had a lot of storms in the eastern part of the basin that interacted with Mexico, and that land interaction is typically difficult to forecast, and obviously results in potentially a lot of larger intensity forecast errors.
Virginia Johns asked, what role do weather buoys play in forecasting, and what is the financial feasibility to add more buoys?
Yeah, buoys are really important, but again, they're pretty sparsely spaced, especially out in the open ocean. So occasionally we'll get really valuable information from one of them if a storm happens to move very close to it or right over it. We get a good central pressure reading or good estimate of the winds, for example. And they're certainly very useful for looking at the outer wind field structure and that broader wind field, sort of the 34-knot wind field of a major hurricane. The buoys can be really helpful in placing that and helping you analyze the structure of that. And they're also obviously critical for the marine forecasting, measuring the significant wave height, which is such an important parameter for marine users. The buoys are very expensive to deploy, and they're also very expensive to maintain. They don't just sit out there and go on for years and years. They have to go out there and be maintained and fixed. So there are a lot of upkeep costs associated with them. And I'll just point out, in the Eastern Pacific, we don't have any buoys in our area of responsibility. So in the Atlantic, and near the Gulf, the Caribbean, near the US East Coast, we have a relatively high number of ocean observations from ships and buoys. In the Eastern Pacific, we have almost none.
And just to follow up on that question, Neil Davies asked, how much do you rely upon buoy data as opposed to, say, satellite data?
Well, the satellite data we have all the time. So we're always going to have satellite imagery. The Dvorak technique, which is the intensity estimate we get from geostationary satellite imagery, is really the basis of most of the intensity analysis for most tropical cyclones globally, except if for our basin when we have aircraft in there, sometimes scatterometer, which is also another type of satellite data. So again, the buoys are useful in certain situations. They're very useful, but a lot of the time they're not as useful just because they aren't in the right place where the storm might happen to be.
And then Kevin De Bruin says, asks, how much does the presence of land affect the wind radii, e.g. the conditions of the Caribbean Sea for a storm above Hispaniola?
Right, yeah, so when we have a wind quadrant that's partially over land and partially over water, we have to draw the quadrant radii to account for the water part. So it's going to be an inherent overestimate over the land areas. And when we have a quadrant that's entirely over land, we're able to shrink the radii down in the analysis and the forecast to represent what's just happening over land. But when you get into areas of topography in the Caribbean, like Hispaniola, what we're trying to depict is sort of the wind field at sea level. So if you get into an area of higher topography, the winds are going to be much stronger at those higher elevations than we're depicting, say, in our forecast, which is, again, sort of a 10-meter above sea level type analysis and forecast.
All right, that's it for now.
Okay, thanks. So I'll go ahead and keep going here and start covering some things with our products. So we have several products that convey uncertainty. The first one and the one that most people are very familiar with is the cone graphic. And the cone graphic tells you the probable track of the center of the tropical cyclone. So it's formed by connecting circles centered on each forecast point that basically encapsulate the average error, the error over the past 5 years, and the 67th percentile of the errors over the last 5 years that tell you that at each of these forecast times, the center position of the actual storm should be inside that circle about 2/3 of the time. That's how they're drawn in a statistical sense. So that for this storm, you'd expect the storm to generally stay inside the cone about 2/3 of the time, which means it's going to come outside of the cone or outside of one of these circles, the center of the storm, about 1/3 of the time. So the cone is not telling you anything about the impacts associated with the storm. It doesn't tell you how big the storm is. It doesn't tell you where the winds are going to be, where the rainfall or the storm surge are going to be. So the cone graphic really only gives you just sort of this big picture idea of where the center of the storm might go over the next several days. So again, there's no information about impacts or hazards. And you can see in this version of the cone graphic from Irma, this orange area depicts the tropical storm force wind field, and the red area depicts the hurricane force wind field. And those both extend well outside the cone initially, because the cone has gotten smaller with size as our track forecast errors have gotten smaller. So that's what drives the size of the cone. And impacts are almost always going to occur well outside the cone in the first few days of the forecast period. Another product that talks about uncertainty information is the forecast discussion that comes out with every advisory package. We talk about our forecast reasoning here. It's where the forecaster can talk about the observations that went into the analysis of the storm, how the model guidance is behaving, what we're basing our forecast on, what's the uncertainty in the forecast. Then we have the ability to put these key messages in here that talk about really sort of the 3 or 4 most important things about the storm. They're very hazard focused. This is back from Hurricane Irma, talking about life-threatening wind, storm surge, and rainfall to Hispaniola, Turks and Caicos in the Bahamas, hurricane watch in effect for Cuba with dangerous wind, storm surge, and rainfall there. And the threat of dangerous major hurricane impacts in Florida continues to increase with a hurricane watch. So again, we're trying to boil down information into these 3 or 4 most important points that we want to get across about the storm from this very high level. And we can talk about forecast confidence in here as well if there's a lot of uncertainty. And then finally, at the bottom of the forecast discussion, we have the table of the track and the intensity forecast that people are pretty used to seeing down there. And we also have wind speed probabilities that tell you the location-specific chances of seeing sustained tropical storm force 50-knot or hurricane force winds. There's a text product version that tells you these probabilities for a fixed set of locations, land areas generally, or islands. And then there's a graphical product that shows you the chances of seeing, again, this version that would be tropical storm force winds at any given location over the next 5 days. So these are point probabilities. So you would look at a point on this map and say at Mobile, Alabama, there's about a 80% chance of seeing sustained tropical storm force winds in the next 5 days. So here's what these graphics again look like for the tropical storm force winds, 50-knot winds, and 64-knot winds. And these come out as part of the standard advisory package every 6 hours for every tropical cyclone. And they are based on the official NHC forecast. And then we create 1,000 different scenarios that are centered around that forecast that use our track and intensity forecast errors that we've made in the last 5 years, as well as a model that tells us the size of the storm, how big are the tropical storm and hurricane force winds. So in this particular example, we have these 1,000 scenarios. If we're interested, and I should mention too that even if the official forecast doesn't take the center of the storm over land, those tracks that do move over land will weaken the storm realistically. So it does realistically account for inland decay. And there is some relationship between the NHC track forecast errors that go into this technique and how much uncertainty there is in the track forecast guidance. So in situations where the models really are in poor agreement, the wind speed probabilities will sort of spread out more away from the official forecast and vice versa. So in this particular example, if we're interested in New York City, we want to know what are the chances of seeing tropical storm force winds at New York. So out of these 1,000 scenarios, there's 590 of them that produce tropical storm force winds. So that means there's a 59% chance of seeing sustained tropical storm force winds at New York City based on the NHC forecast and the typical uncertainty in that forecast. We also have products based on the wind speed probabilities that convey uncertainty in the time of arrival of tropical storm force winds. So it's using the timing information from the wind speed probabilities about when will sustained tropical storm force winds start at a given location. So there's 2 versions of this, an earliest reasonable and a most likely time of arrival. And these lines on here are showing you those times of arrival at given locations. And then there's a version that actually shows the tropical storm force wind speed probabilities underneath it. So this earliest reasonable arrival time of sustained tropical storm force winds is the time that you can generally assume is going to be safe from seeing sustained tropical storm force winds. There's only a 10% chance that the tropical storm force winds would start at a given location before the time indicated on this graph. So for example, here with Lorenzo, in this area here over the east central Atlantic, there's only a 10% chance that tropical storm force winds would start here before Saturday at 8 p.m. And this is the best graphic for users that have a low tolerance for risk. If they want to make sure they're out of an area or have their preparations done, and they want to be really sure that the tropical storm force winds haven't started yet, this would be the graphic to use. We also have a most likely time of arrival graphic that shows, again, the most likely time that the tropical storm force winds will begin. And that's, again, the time at which there's an equal chance that the winds will begin before or after that time. Again, I mentioned the key messages. This is going back to Irma. Again, we have the ability to sort of boil down the hazard information into these 3 or 4 key messages that try to really get on the hazards and the impacts in given locations and try to provide some preparedness information as well to folks in the path of the storm. Here's the potential storm surge flooding map or inundation graphic, again, that accounts for uncertainty in the forecast. It's really a quantitative risk assessment graphic for people who are making decisions about evacuations or other storm preparations. So this graphic is first issued when an initial storm surge watch goes up for the United States, and it shows the height above ground that the water could reach. It's not what it's expected to occur, but it's a reasonable worst case scenario for storm surge inundation at any given location. So this is the value of inundation that only has a 10% chance of being exceeded based on the NHC forecast and the typical uncertainty in the intensity, track, and structure of the storm. So again, this is going to be available about 60 to 90 minutes after the advisory comes out, and it's first available when a storm surge watch is issued. We also have a storm surge watch and warning for the US that we issued, and this is more of a public product, and we want to get people to sort of respond to their instructions from their local officials, help guide emergency management evacuation decisions by highlighting these areas that have a risk of life-threatening inundation for storm surge, and that generally begins at 3 feet of inundation or more. And this is the storm surge watch warning for Hurricane Florence for the coast of North Carolina in the dark pink, and there's a storm surge watch in effect for these light pink areas as well. The watch is typically issued 48 hours before the arrival of life-threatening surge, or if the tropical storm force winds are going to arrive first, it would be issued 48 hours before those winds begin. And the warning is typically issued 36 hours before the onset of hazardous conditions. And this storm surge watch warning is really a collaboration between the Hurricane Specialist Unit, the Storm Surge Unit, and local National Weather Service forecast offices. Just to real briefly touch on hurricane watches and warnings, a hurricane watch means conditions are possible somewhere within the watch area, generally within 48 hours. The hurricane warning means hurricane conditions are expected somewhere within the warning area, generally within 36 hours. And again, similar to the storm surge watch, the hurricane watch and warning lead time is tied to the arrival of the tropical storm force winds, because that really marks the end of any preparation time for the storm. So you want to give people that 36 and 48-hour lead time relative to the onset of those wind hazards. So when we issue warnings, we're basing them on the forecast track, the size of the storm, and then the uncertainty in the forecast. So we're not just going to put up a warning for the exact area that our forecast puts hurricane force winds over, because 36 hours out, you remember our average track forecast area goes up about 40 nautical miles per day. So 36 or 48 hours out, we might be dealing with 60 or 80 mile uncertainty in where the center of the storm is going to be. And if you add to that the uncertainty in the size of the hurricane force wind field, you're going to draw a much larger watch or warning area because of the uncertainty in the forecast. And again, remember, the watch and warning mean that those conditions are expected somewhere in that area, or possible somewhere in that area, not the whole area. And then again, the orientation of the forecast track of the storm relative to the coastline plays a really big role in how big the warning area is going to be. For a situation like this, where the track is relatively perpendicular to the coast, the warning area will be a lot smaller than a track parallel to the coastline, which puts a much larger area of the coast at risk from seeing those winds. When we issue watches and warnings, we're trying to maintain continuity with the watches and warnings that are already out. We're trying to gauge the expectations about how much the forecast is going to change. Are we trending the forecast to the left or to the right, or stronger or weaker? And what's the forecaster's assessment of the uncertainty? The vulnerability of the area potentially affected can also play a role, and the time of the day or day of the week could play a role in when we might go ahead and issue that watch or warning. We don't really like to issue watches and warnings at 11 p.m. at night. That doesn't really give people a lot of lead time at that time. So we're typically much more likely to issue them at 5 p.m. than 11 p.m., for example. Now, we issue the coastal watches and warnings for the United States from the Hurricane Center, but internationally, we recommend the placement of watches and warnings to each of the countries in our area of responsibility, but they have the ultimate responsibility for issuing their watches and warnings for their country or islands or jurisdictions that they're responsible for. So this is just a map of the Caribbean and the different countries that we coordinate with, and the different meteorological services that we typically coordinate by phone and email throughout the region that we cover. I do want to touch on potential tropical cyclones. This is a concept that we started using in 2017 that allows us to start advisories and issue watches and warnings for land areas before a tropical cyclone is actually formed. So we used it 18 times over the last 3 seasons, 6 times per year, much more than we initially thought we would. And in the past, before we had this capability, we had to wait till a tropical depression or tropical storm formed before we could start issuing our advisory products, and before we could issue, say, a tropical storm warning or a hurricane watch for a portion of coastline. So now with this capability, we provide an average of about 17 hours of additional lead time on watches and warnings. We used this last year for what became Barry in the Gulf of Mexico. We issued a hurricane watch for a system that hadn't even become a tropical depression or tropical storm yet. So again, it allows us to issue the watches and warnings with that appropriate lead time for systems that are not quite tropical cyclones. And we do issue them through the standard suite of advisory products. We've talked about what sort of service might be needed for the marine community. Again, in advance of tropical cyclone formation, right now these are focused on the issuance of watches and warnings for land areas. So we'd be interested in thoughts about what the trigger might be for this service for the marine community. Quickly cover product changes for 2020. We have a new 60-hour forecast information within our advisory packages. So this started, this is Tropical Storm Cristobal back in June. You can see there's a 60-hour forecast point on the cone. This 60-hour track and intensity and forecast size information is really useful for the probabilistic storm surge and wind products. It's also helpful when we have a storm that's going to be near land in that 60-hour time frame, or there might be some change in the intensity or track that we want to be able to depict in the forecast. You'll see that 60-hour forecast information here in the Tropical Cyclone Forecast Advisory, and then also in the Tropical Cyclone Discussion Table. So we have the position, the intensity, and the 34 and 50 knot wind radii. The new experimental peak storm surge forecast graphic has been rolled out this year, and this is a sort of a visual representation of the peak storm surge inundation that we put in the public advisory. It's been in our text products for years, but now there's a way for us to graphically depict it. And again, it's an aerial threat. It's the expected value somewhere within that specified area. So this is a graphic from Cristobal. So somewhere between the mouth of the Mississippi River and Ocean Springs, Mississippi, you should see 3 to 5 feet of inundation, assuming that the surge occurs at high tide. And this is really a graphic for media, social media, sort of large scale briefing applications when it's not appropriate to zoom down to very high scale, high resolution, local scale inundation mapping. So we're interested in feedback and comments on this graphic this year. A new change for products in 2020 is new local time zones that are being used for our advisory products in the far eastern part of the Atlantic Basin. For air systems that are located south of 25 north and east of 30 west, the public advisory, the discussion, and most importantly, the time of arrival graphics will be in Cape Verde time. And for systems located north of 25 and east of 45, those products will all be in Greenwich Mean Time. And this was done primarily because things like the time of arrival graphics aren't terribly useful to customers in these parts of the basin if the time zone shown on those products is 3 or 4 hours different from the local time in those affected areas. So you can see that if Eastern Daylight Time is 11 a.m., Cape Verde time is 2 p.m., GMT is 3 p.m. So this will help those customers and users in those parts of the basin to have products that are more closely aligned with their local time zone. Once systems get west of 30 west in the deep tropics, the time zones will go back to what they've always been. Looking ahead, I want to touch on some possible future products that we're looking into. We're doing experimental day 6 and 7 track and intensity forecasts. We've done those for 3 of the last 4 seasons in the Atlantic and in the Eastern Pacific. Here's what the Atlantic results look like. You can see the track forecast error in blue shows this pretty linear increase all the way from 5 to 6 and 7 days. Not surprisingly, the average errors look pretty good. However, the average track forecast error at day 7 is 267 nautical miles, but we have these outliers, these storms that have really large track forecast errors at day 7. We have about 8% of them have errors of greater than 500 nautical miles. So again, those are these such situations where either the steering flow is going to be very poorly forecast, or there's some problem with the structure of the storm. When you get out to those time ranges, you can have these really, really large track forecast errors. So that's one reason why we haven't gone public with these forecasts yet. And you can go back and look at a situation from Florence where we had a day 7 forecast that we were making experimentally in-house on September 4th when the storm was out here well in the tropical Atlantic, far away from everybody. But at day 7, all the models were showing the storm recurving well east of Bermuda. And we ended up with a day 7 track forecast error of about 675 nautical miles compared to where the storm was at the time. It ended up verifying. So if this had been a public forecast, how might it have affected decisions made by the marine community or other users that might be affected by Florence? So this is a real challenge as to how to depict these longer range track forecasts, and hopefully some social science work will help us with that. We also don't have a lot of guidance at day 6 and 7. The track guidance is generally limited to the global models. We don't have much intensity guidance either. We just now this season are getting some statistical intensity guidance at day 6 and 7, but this is the first year we've had that. And what we're interested in from the marine community and other users, what sort of uncertainty information would be useful given the average track and intensity errors at these very long time ranges and the possibility that you can have these sort of very large outlier track errors that I showed, again, those ones that are greater than 500 nautical miles, for example. We're also making 7-day Genesis forecasts. As I mentioned, the tropical weather outlook has a 2-day and a 5-day probability of formation. We're also experimenting with a 7-day Genesis probability. We did this last year for the first time. The Atlantic, this is what's called a reliability diagram. So perfect forecast would lie right along this black diagonal line. So you can see that our forecast had a bit of a low bias at the low probability. So storms that we were forecasting to have a 20 to 30% chance of formation formed 50 or 60 or 70% of the time. And the storms that we were forecasting to have a 60 or 70% of a chance of formation formed only 40 or 50% of the time. So we had sort of a rough year in the Atlantic. Not surprising, the farther out you go, the probabilities are going to be more difficult to discern. The signals in the models are going to be harder to work with. But in the East Pacific, we had a really successful year. We had really reliable forecasts that were very close to where the verifying percentage of storms that developed were very close to our forecast probability. So we're going to continue with that going forward as well. I'll wrap things up. I've got a few more minutes for some more questions. So thanks again for having me today. Amanda?
Okay, hi everyone. I know people said that I was a little garbled, so hopefully you guys can hear me this time. David Disbrow asked, going back to the buoys, what resource may I use to find the lat long of international buoys?
I think you can go to the National Data Buoy Center webpage, and they have international buoys on their website, so you should be able to click on them and see where they're located there, at least most of the standard type weather type buoys.
Okay, what were the issues and the errors encountered with Dorian?
Dorian was complicated. There were multiple sources of error there. The track and intensity forecast errors were kind of linked together. Early in Dorian's life cycle, it looked like the storm was going to move into the Caribbean Sea and then pass near or over either Puerto Rico or Hispaniola, which would have significantly weakened or maybe even entirely killed the storm off. But the storm sort of did a northward jog across St. Lucia and reformed and then went off to the right and missed Puerto Rico to the east and didn't come anywhere close to Hispaniola. And because of that, we had some really large intensity forecast errors. We had been making intensity forecasts assuming that the storm was going to move over the land masses. And then the storm didn't, and it encountered this very favorable environment and went on to rapidly strengthen Category 5 status in the Bahamas. And we actually had a day 5 intensity forecast error of 100 knots, which is the largest day 5 intensity forecast error we've ever made. And that was, again, one of those forecasts where we got the track wrong. So the intensity forecast had no chance in that particular case. So Dorian was a very challenging storm from that perspective, and then also from the fact that it had that stall out over the Bahamas and how close it was going to get to Florida. The average track forecast errors for Dorian, once it got to the Bahamas and near Florida and the East Coast, were really very small. But even a 30 or 40 nautical mile error makes a huge difference when it's the difference between the storm staying offshore and making landfall.
Okay, Haram Iskabi asked, how does radiosonde data help with storm location accuracy and forecast, especially when there's radiosonde soundings every 6 hours?
Yeah, the radiosonde data really are used for the numerical models. They help, again, initialize and better understand the steering flow, and that's why we sometimes ask for them every 6 hours. We've had some studies that have shown they've been pretty beneficial in certain cases, although we need to do more of those studies to get a better sense. But we do look at the radiosonde data ourselves as human forecasters, and we look at things like the moisture, the shear, the wind profile for tracking disturbances, and also for looking at the environment affecting ongoing tropical cyclones. So they're really valuable pieces of data.
Okay, what are the best products and forecasts for storms that emerge close to your location? For example, if you're going from the Outer Banks and arriving at Norfolk, Virginia, the 5-day graphical forecast is showing a possible system emerging at 80%. What's the best way to understand possible impacts to us here when the storm is likely to form within 24 hours?
Right. These are tricky. When you have systems that haven't quite formed yet, I would probably steer you to the products from your local National Weather Service office. They're going to have the best handle on the local conditions and what's going on in the sort of nearshore waters and even on land areas in that area. So we're coordinating with them. For a system like the one ongoing now, the winds are not going to be a big impact, at least in that part of the area. I don't think it's going to be a tropical storm, maybe until it gets a little farther north. But the rainfall certainly can be dangerous marine conditions. So those are going to be accounted for in the marine forecast and other products from your local weather service office.
Mike, several people are saying now you're garbled, and I was before. Yeah.
Let me see if I can, if I should try to drop off and come back on. Let me try that real fast.
Thank you, everyone, for being patient.
Okay, I'm back. Hopefully the audio is better.
It sounds better on my.
Okay, great.
Okay, back to questions. Edward Max Stovall asked, how important is BOSS weather reporting to models?
BOS, is that what he's asking? Yeah, the ship observations are really helpful. I mean, obviously we don't want you guys near storms. Hopefully you're staying away from them, but any observations we get, for tracking waves, for tracking disturbances, knowing what's going on in the periphery of the storm are really, really useful, again, because we have such a dearth of surface data over most of our area of responsibility, especially out on the sort of open ocean. They're really, really helpful.
Caroline Johnson asked, as an ocean sailor, it would be great to get a deeper dive into modeling and forecasting process. And will this webinar be available as an archive recording?
Yes. Yeah.
And what can Steve Hodges asked, what can public users do to encourage a continuation of NHC product availability and development?
Well, I think part of it is just when we have new products out there, we're trying to incorporate more social science into the product design. For a long time, we made products that we liked as physical scientists because we thought they were useful for us, but we found out that they're not necessarily useful for people to use. So if you have an opportunity to participate in any sort of ever focus group or provide feedback on experimental products that we have on our website, or through anything, some sort of outreach event from your local National Weather Service office or local emergency management, that's a great way to provide feedback to us. And again, we're always interested in the feedback and how we can make products that are, again, more useful for people to make decisions with.
And what is the best way for mariners to send you weather observations?
Well, VOS is probably the best way. That's going to get into our, computer display systems through things like AWIPS. Chris might have more details on how to get to VOS, but I'd suggest you talk to your port meteorological officer. They're going to be the person that's going to have the information about how to get involved with VOS and make sure that the data gets to us and to others.
Jeff Ziedzik, sorry if I butchered that, is asked, is it harder to predict strength of storms as they get close to New England?
In some ways, storms that get that far north, the intensity forecast errors actually get a little lower because there's not as much of a chance of rapid intensification, which is one of the things we struggle the most with. Typically, storms that are that far out of the deep tropics are going to be steady state or maybe slowly weakening. So we tend to have maybe a small high bias in our forecasts up there, but we don't have a lot of forecasts in that part of the basin, so it's hard to tell how the statistics change over the years without going back a really far, long period of time, and that may not be representative of what we do now. But typically, the intensity forecasts get a little easier as you get out of the deep tropics and don't have to deal with that rapid strengthening.
And then the last question from Lou Fincher, how much weather information do you receive from the offshore platforms?
Like oil rigs and things like that. Is that what he's asking about? Yeah, we get observations from a lot of those platforms routinely, so they are really useful. The challenge with them is they're not really representative of a surface or 10-meter wind, so they're elevated sites, so we have to sort of do some mental calculations to try to figure out what that actually means in terms of the surface data, which is what we're most interested in. But yeah, we're certainly interested in everything we can get our hands on, especially out over the water. There's just not much, so anything we can get is very appreciated.
And actually, we have one more question that snuck in from Neil Davies. Do you have products available for mariners at sea, such as ways to get data with low bandwidth methods, like a satellite phone?
Well, some of our products, like the forecast advisory, go out on standard sort of marine dissemination platforms. And I know TAFB has a low bandwidth forecast page, and their forecasts get out that are, again, more tailored to the high seas forecast, for example, and some of the graphics for marine users. So that's going to be the best bet, is to go through those sort of standard marine dissemination channels. And Chris may touch on some of that tomorrow's webinar.
All right, that's all the questions.
Okay, great. Well, thanks again, everybody. Really appreciate the great attendance and the questions, and thanks for the time. And if you ever need to contact me or have feedback on our products, my email address is on the last slide of the presentation, so feel free to drop me a note. Thanks.
And can you follow up to where people can get this presentation after we're done recording?
Yes, we can. Yeah, we'll try to send an email out to the participants and make sure that they know. I'm not sure exactly where it's going to be posted yet, but we can find out.
Okay, great. Thanks.
Yep, thanks.